So today I'm going to talk a little bit about sort of doing safety for autonomous vehicles. And the way that I always like to start these kinds of talks is to describe just how difficult this problem is. And the best way to do it is by looking at human stats. So these are statistics from NHTSA up until 2014. The numbers actually beyond 2014 actually don't look that much different than what's plotted here. So this is the number of fatalities per 100 million miles driven in the United States. And over here, all the way on the left-hand side in 1920, we're about 24 fatalities per 100 million miles driven. And all the way down here on the right-hand side, here 2013, you see we've gotten down to about 1.1 fatality per 100 million miles. That is extraordinary. Humans are really good at driving. And a lot of the safety results we have in driving are from obvious things, obvious in retrospect, like things like traffic lights, speed limits, and those things seem really obvious. But I would say if you've ever driven to India, it's not so obvious. As we start moving along the x-axis here, we start getting, sort of more invasive types of safety measures like seatbelts, airbags, anti-lock braking systems, electronic stability control. We're starting to move towards these places where it becomes really hard for us to think about safety because we're going to have to start imbuing systems with safety by having them be active. And so it's not a surprise that, down here in the 2010s, we're starting to think about autonomy. The thing to keep in mind is, despite us starting to think about, developing autonomous features even, in the 90s here, maybe even earlier than that, it's not been, very long that we've actually been able to, go out on the road and do testing and do diligent verification of how, autonomous and how safe our systems are. The world leader at the moment is probably Waymo. They've done a hell of a lot of driving. This is starting in 2010, approximately. They've been driving up until about now. This is from last year. They've driven about 10 million miles. And in fact, they slowed down a little bit because of the pandemic, but they're back on the roads and they're doing really exciting things. But in fact, they just haven't driven enough in the real world for them to really say very much about the safety of these systems. And so the question I have is, how can we start thinking about verifying the behavior of these systems without resorting to simulation? And what I mean by simulation is, going out in the real world and driving lots and lots of miles. It's an expensive proposition. Can we, see how far we can bring along, control and verification to say something about the safety of these systems? So to understand how to do that, we need to first think about how planning and control work. And usually planning and control are arranged in sort of a hierarchy here. And the top level of this hierarchy is a high-level planner, which is doing something like a Google Maps style thinking of the world, which is, I go down to, Gailey, I make a right, and then I go further down and I get on, 405, et cetera. Well, all those turn-by-turn instructions are handed to a trajectory planner that tries to follow those different types of instructions. And subsequently, that information is passed to a tracking controller, which actually, takes advantage of the Powertrain model and all sorts of other stuff to design a controller that is able to follow a particular trajectory. The question people usually ask is, why do we think about breaking down planning into these three different levels? And the reason is, planning needs to happen fast. And so if you're in an environment like this one and you just sort of pause and you're thinking about how to do planning, you're just going to decide to never move. You really need to be able to plan quickly. And planning with a model like a Powertrain model, which is really, really complicated while doing planning, it means that you're going to have to manage a few hundred dimensional model while doing planning. And that can be really, really hard to manage while being able to say something about safety and real-time performance. So, given this sort of model, the question is, what do people typically do? And sort of the standard in this area has really been thinking about the trajectory planner and tracking controller sort of layers together. The way that's typically been done is by using something called model predictive control. And so, for example, the trajectory planner could be generated by, some sort of nonlinear model predictive control method, and the tracking controller could use some sort of linear or, quadratic programming-based model predictive control scheme that tries to, generate a tracking controller that achieves some satisfactory performance. In fact, this has been going on for some time. This is actually when I was doing my PhD. It's actually my first time in Michigan. We went up to Sault Ste. Marie, which is a very, very cold part of Michigan. And we were working with Ford back then and doing this sort of planning fully autonomously and really managing those two levels. And this is, I think, doing about 30 meters per second or maybe 40 meters per second, no, 30 meters per second, lane change maneuvers fully autonomously on snow. And the really cool thing is you can get this to work fairly reliably. The challenge is that sometimes things don't work out really well. And this is me sitting in the back seat now. And in a moment, it's going to go autonomous. And you'll see that actually we're about to crash into a snowbank here. And it's a very expensive vehicle that we just broke. So the question is, how can we start imbuing these systems with some notion of safety? And typically that's been done at the sort of tracking controller level. And there's been a variety of different methods that have been proposed to sort of accommodate introducing safety while doing path planning. So I'm going to sort of categorize these methods before describing the method that I'm going to spend the rest of the talk talking about. So the first set of methods is called check methods. And what they try to do is to just perform collision checking for a pre-computed trajectory. These have been done in the past by using these types of zonotope methods. And the way to think about it is as follows. So suppose I have this sort of road and I have a particular pre-computed trajectory. Well, what I can then do is basically, try to follow that trajectory by using some sort of tracking controller, but inevitably there's going to be some error. Well, what I can do then is to bound the difference between my vehicle following that trajectory and the one that is, that actually is realized by, using this tracking controller and accommodate that tracking error. Essentially, I generate these sort of boxes or zonotopes. And what I can try to do then is to verify that those zonotopes don't intersect with bad parts of the environment. And it turns out that that is something that can be done fairly quickly. The challenge is that planning with this kind of method, not just pre-computing a trajectory and holding on to it, can be a big challenge. So to address this kind of limitation, there's been a family of methods to basically modify control inputs or tracking control inputs to ensure safety, and I call these class of methods correct methods. And in fact, there's been a variety of methods proposed to address, satisfy this requirement. I think Aaron spoke on Monday, and I'm sure he spoke a little bit about these control barrier function methods. They're really powerful. There's other classes of methods like fast track, which maybe Claire Tomlin spoke about a few weeks ago. I think she was here. Anyway, these methods do really beautiful work in modifying a control input to ensure safety. Let me illustrate how these work again by going back to this model world. So again, let's think about control barrier functions. What they do is they basically, have the space of control inputs here on the left-hand side. They have a particular, trajectory that's been pre-computed here. And what they do at runtime is basically generate a safe set here that's drawn in green. And at runtime, they solve a quadratic program to essentially correct control input so that they fall back inside of this polytope, which is described nicely. These methods are really nice. However, they're just doing modification of a particular control input at a particular instance in time, which tends to make them a little bit conservative. On the other hand, fast track, this method developed by Claire Tomlin's group, is a really cool idea where they treat sort of this trajectory planner and this tracking controller as two different agents that are competing against one another. And what the trajectory planner does is generate some sort of trajectory. And what the tracking controller does is basically try to generate the best tracking controller that can follow the worst case behavior of this trajectory planner, and that generates this type of cone. And what they do is say, well, look, this cone can look as large as this red region on the left-hand side. And they essentially take that red set and they essentially buffer all of the obstacles that exist in the world with that buffer, which is drawn in red, and essentially try to do planning while remaining outside of that buffer. That's a really powerful idea. And in fact, you can solve this sort of multi-agent sort of game by using things like Hamilton-Jacobi-Bellman, which has been a popular thing at IPAM in the past, and probably will continue to be a popular topic. The challenge is that by treating it as a two-person game, you're essentially dealing with sort of these worst case behaviors, and that can make things like fast track conservative, which I'll illustrate later on in the talk. So what I'm going to describe here is introducing safety one level higher, and that method is going to live at this trajectory planner level. And I'm going to describe two different methods for doing this. The first one are these funnel library methods. And the next one is this reachability-based trajectory design, which is what I'm going to speak about today. And both of these papers are in IJRR, but this bottom one is the one that's going to be the focus of this work. How does the funnel library one work? Well, it works like this. I'm going to select a bunch of trajectory parameters on the left-hand side. Each of those trajectory parameters are going to be associated with reference trajectories on the right-hand side. And now what I'm going to do is basically describe this tracking error by computing a reachable set that looks like a funnel. And essentially at runtime, what I'm going to do is pre-compute all of these funnels for all of these pre-computed trajectories, a finite number of them. Essentially, if I have an obstacle that appears in the environment, I'm just basically going to eliminate examples from this trajectory parameter space and just choose the one that is safe. Now, the problem with this funnel library method is that the collision check is not verified to operate safely, and I have to pick a finite library. And what this reachability-based trajectory design technique is going to do is going to do reachability across a continuum of trajectory parameters with trajectory-dependent error, and that's going to be done offline. And I'm actually going to show you how to do obstacle discretization to ensure real-time validation, and that's going to run online. And that's the method that I'm going to speak about today. So that's going to be sort of the three sections of my talk. I'm going to start off by speaking about it in the static world, then the dynamic world, and then I'll conclude. This may be a good moment to take any questions if there are any. I see a chat question. Oh, never mind. Okay.
No, I think we're good to go.
Okay, awesome. So static. So what we're going to do is we're going to parameterize trajectories. And the way that's going to work is as follows. I have my differential equation. And my differential equation is going to be a function of a trajectory parameter, which is going to correspond to a specific closed loop control input that I'm going to apply into my system. I'm going to, describe an example of a trajectory parameterization. You can choose any type of trajectory parameterization and actually apply reachability-based trajectory design. The one requirement is that the trajectory parameterization brings you to a stop, and that's what's described here. We're planning over a finite horizon, and eventually the trajectory parameterization brings us to zero speed. Okay, so we're going to choose this type of trajectory parameterization, for example, and that would correspond to doing a lane change. Okay, so each trajectory is defined over a finite time interval and ends with a fail-safe maneuver, which is something like braking in this instance. So now what ends up happening is that, when I apply this trajectory parameter to my system, I'm inevitably going to have some sort of tracking error associated with it, which is going to be described with this dotted line. And in fact, I can do this for a family of trajectory parameters, which is this light blue set over here on the left-hand side. And each of those is going to, generate a possible trajectory that my system is now going to try to follow. So the first thing we're going to assume is that we have a way to bound the worst case behavior across all of the different trajectories that we've chosen, and we can bound it in its integral using this function g. What do I mean? Well, in particular, if I have my full vehicle model and I have sort of this trajectory producing model, the difference between these two in the two spatial coordinates, x and y, is going to be bounded by this integral of g. Okay, so in fact, this assumption is basically building a type of bisimulation relationship between my vehicle model and this trajectory producing model. And in fact, what we can show is that there are really nice ways to build this type of g function. You can take a look at some papers that have been written on this topic, including by myself and by Murat Archak's group, but there are nice ways to actually build this for ground vehicle models, it turns out. In fact, we've actually extended this to quad rotors and other types of vehicles as well. The important thing is with this g, what you can do is basically introduce a disturbance term. And that disturbance term, if you allow it at any instance in time to take values between -1 and 1, well, in fact, what you can do is compute a forward reachable set for this entire system. And what you can show is that any trajectory produced by this model with this trajectory parameter is going to live, if it's followed by the full vehicle model, is going to live inside of the forward reachable set of this whole system. And that whole system's error is going to account for any type of tracking error that may occur while following that trajectory producing model. So the question is, if I can generate these sorts of forward reachable sets for my system across all of these different trajectory parameters, and I could parameterize them by the trajectory parameter, well, then I could use that while saying something about the safety of the system in real time. So the first question is, how do I actually compute this forward reachable set that is a function of the trajectory parameter? And to do that, we actually apply sums of squares programming. And the way that it's going to work is that we're going to write down an optimization problem over the space of functions. And so I have three functions, w, v, and q. And in fact, what we're going to do is show that this w is actually going to converge to the indicator function on the forward reachable set of the system. And in fact, it's going to be a trajectory parameterized forward reachable set. Okay, so I'm going to be able to take super level sets of this w function and use that as a representation of my forward reachable set. To do that, what I'm going to do is write down these two conditions on the function v. These two conditions look a lot like Lyapunov function conditions. In particular, I'm assuming that this Lyapunov function, because of this negative sign, is actually decreasing along trajectories of the system. Okay. But in fact, I need to be able to account for the fact that I have disturbances, that is that function g, which is describing the difference between my trajectory producing model and what my vehicle is capable of realizing. And to describe the effect of those disturbances, I'm going to introduce this function q. And q essentially incorporates that uncertainty or disturbance function d that I described earlier. Well, in fact, then you could write down this final condition. This final condition is actually ensuring that if you solve this optimization problem on the left-hand side, for any point that belongs to the forward reachable set, wx of k is actually going to be greater than or equal to 1. What does that mean? It means that if I could find a feasible solution to this optimization problem on the left-hand side, well, any w that's feasible with respect to this optimization problem is actually going to be an outer approximation to the forward reachable set for this system. Why is that useful? Well, in particular, if I could hold on to that forward reachable set and I chose a particular trajectory parameter like I'm doing on the left-hand side here, well, then in fact, if I looked at the W superlevel set, one superlevel set, I would actually get a representation of the forward reachable set. So in fact, I can do that across a variety of different trajectory parameters, and I'm essentially getting these nice looking curves that describe the forward reachable set of the system. Now that optimization problem on the previous slide, it's actually an optimization problem over the space of functions. In fact, you can use semi-definite programming to actually find a nice convex representation for that optimization problem that has a bunch of really nice properties. And in fact, I won't describe that here, but you can show that that semi-definite program will actually, as you increase its fidelity, will actually converge to the true solution of that optimization program on the previous slide. Okay, so now that I have this sort of function representation that parameterizes the forward reachable set, the thing that I want to do online is that I get obstacles like this thing on the right-hand side, and I want to identify the set of unsafe trajectory parameters. And in fact, I can write down an optimization problem to do that. So I'm going to minimize some cost function that is going to be some cost function over the space of trajectory parameters such that wx of k is less than 1 for all points that are on the obstacle. This condition is essentially ensuring that my forward reachable set doesn't actually collide with any obstacles that exist in the environment as a function of the trajectory parameter that I've chosen. That's amazing, because this is a nice optimization problem to write down. And in fact, we can actually represent even this constraint down here, this for all x, as a semi-definite program. And so what that means in practice is that I can write down a really nice optimization problem that I can solve. It could be convex in practice if I want to solve. But the challenge is that it runs extraordinarily slowly, which means that I'm not actually operating in real time. So you can represent obstacles, for example, if they're squares, as boxes. And in fact, it'll take on the order of about 18 seconds to solve this optimization problem. But if I want to intersect with this box, I could instead just represent it as a sequence of lines that describe the exterior of this box. And now we see that that operates at about 1 second. That's still not very quick. So we've gone boxes, lines. Maybe the last idea here should be points. Maybe represent that obstacle as just a set of points. And that idea is a really smart one, but it turns out to be problematic. And let's see why here. So if I have my obstacle here on the right-hand side, I can map that to an unsafe set of trajectory parameters here on the left-hand side. And now I can discretize my obstacle as a set of points. And the problem is that that generates an inner approximation to the set of unsafe trajectory parameters, which means that if I live outside of that discretized representation of unsafe trajectory parameters, I may not actually be safe. Okay, so this is a problem for us. So how do we actually ensure that we can ensure safety or guarantee safety in this situation? Well, one way to do that is to buffer this obstacle by some amount and then choose points on the buffered obstacle's exterior. And in fact, in that instance, hopefully you can actually get an outer approximation to the set of unsafe trajectory parameters, in which case you could actually make sure that you're actually safe if you operate with this discretized representation. And in fact, we've shown in this IJRR paper that if the vehicle itself is convex and the obstacles are buffered by a distance b, there exists a constructive way to build a point spacing R that can be pre-computed offline that generates an outer approximation to the set of unsafe trajectory parameters. In fact, the way that it's going to work is as follows. So suppose my vehicle has a width W. Well, what I can do is buffer my obstacle by some b that is going to be between 0 and 1/2 of the width. And if you do that, you can actually show that if you make the point spacing less than or equal to 2b, that in fact the obstacle will truly represent, or the discretized obstacle will truly represent safety. And what that'll look like is an outer approximation here. And in fact, that gives us this really nice theorem down here. So we've now applied semi-definite programming, and we've applied this technique where we've discretized our obstacle representation to ensure safety. The question is, how does this actually work in practice? And that's where we can start with some demos and illustrate how this performs. So we're going to show a lot of these videos. So I'm going to go through a little bit of a legend here just to make sure everyone is comfortable with this. We're going to have the robot's planning view on the left-hand side here. We're going to have a camera usually on the robot. We're going to have, let's say, a mock road and random obstacles that's in the real world over here on the right. What we'll have are these waypoints that are generated by our high-level planner. Those are, again, these turn-by-turn instructions. We'll always represent obstacles as red. Okay, these will be directed using some sort of perception engine. In this instance, we're using LiDAR. We'll have a robot footprint that's drawn in blue here. And then we'll have the control parameterized or trajectory parameterized reachable set that's going to be drawn in green. Okay, so we'll show you this video that's running, when we used to have a lab. And you'll see, again, all of the planning is happening on board. This vehicle doesn't know anything about the obstacles until its sensor footprint actually gets close enough. And you're going to see, they'll start moving stuff around, and you can still get this vehicle to operate safely. And it's making all the decisions on board the platform at runtime. And it's actually able to ensure safety. And my students will kick around and do some more stuff. If you want to look at more videos, take a look down here at this YouTube link. In fact, the first thing we did after we generated this algorithm was actually compare it against a bunch of different alternative algorithms that had been popular in the literature. And we did it in about 10,000 different scenarios using that vehicle model that I had described there. We gave, because we're going to be doing receding horizon planning, gave our planner 0.5 seconds to generate a plan. The LiDAR had a footprint of about 4 meters. We ran RTD, which is our method. We ran an RRT, and we ran nonlinear model predictive control. And we used a sort of standard method for nonlinear model predictive control using GPOPS2. If you're interested, happy to jump into the details. Turns out for that last method, 0.5 seconds is insufficient to generate a plan. It's just too slow to be able to generate a plan in real time. So it never moves, which means it never gets to any goals. It never crashes either because it never moves. The RRT, which is a popular method, does pretty well in reaching a bunch of goals, but it does crash fairly often. Whereas our method is able to balance between these different two. It always is safe, but it's able to reach goals. The next thing.
I had a quick question on the RRT side of that. Mm-hmm. So I remember 10, 15 years ago in the Urban Challenge that a lot of folks really loved the RRT because they said it almost always finds the same solution that NPC finds. And I had my doubts, but I wasn't in charge of that part of the project. So, so I'm curious here, it seems like a lot of crashing when it otherwise may just want to stop. And so is there something implicit in RRT that it just doesn't want to give up and admit failure?
Yeah, that's a really good question. So I should mention, we did a bunch of tuning because we couldn't really believe that this RRT was this crappy. So I should mention that. In the code, I'll cite a reference at the bottom. You guys can go and play with the code. We've made everything publicly available because, we were unsure, right? What I would say is that the RRT, if really well tuned, can do reasonably, comparably to nonlinear model predictive control in very specific scenarios. So in this scenario, actually the environment is going to be pretty unstructured. It doesn't look like that road scenario that I described earlier. It's actually going to look like another picture that I'm going to show next. And in those types of unstructured scenarios, the RRT does okay. It's just that, it tends to be aggressive, and RRTs are not usually meant to be run in a receding horizon fashion. So usually they're kind of tuned or built for these sort of manipulation tasks where you're imagining that you know everything about the world before you run anything. So typically in this sort of ground vehicle world, people have moved away from RRTs and gone to state lattices, which I'll describe later. And that's sort of a blend of sort of a nonlinear model predictive control method with an RRT style thinking of the world. And so those methods do perform okay. What I would say is you're really relying on the fact that you've pre-computed lots of stuff, and they can work okay in simple environments where you're not behaving very aggressively, but tend to sort of crumble under the pressure of having to operate sort of with a real-time sort of burden on top of you. Okay. Does that answer your question, John? Okay. So the next thing we did was we wanted to compare it to Fast Track. And so this is Fast Track actually running. What it does, and I'll play this video again, is it basically is making a decision. Oh, yes, there you go. It's basically making a decision that's just arbitrary until it gets to an obstacle. And then you see these dotted lines that are describing, a buffer that it's going to, start being careful in and around about. And when it falls within a buffer, it basically doesn't know what to do anymore because it doesn't know how to choose a safe plan that stays outside of a buffer. Our method, on the other hand, does much better here. The buffer doesn't have to be very big, and so it can actually behave really aggressively here and actually get to a goal. And so we've actually done a pretty thorough comparison here with Fast Track. Happy to share the code. The next thing we did was actually take a model of a full Powertrain Ford Fusion that we actually have at Michigan, and we actually ran it on a test track in Michigan, which is called M-City. CarSim has a full Powertrain model, all sorts of complexity and whatnot. And so you can actually take it and apply it in simulation. The speed limit of this test track is around 60 kilometers per hour. And in fact, what you can see in this test track is that RTD is making decisions that are totally reasonable, like slowing down around curves and basically speeding up on straightaways and making smart lane change maneuvers. That's all autonomously done. We are not making any of those decisions for it. It is just deciding that that is a smart thing to do. And again, you can find this video down here on the right-hand side. If you want to play around with it, please feel free to go take a look there. In fact, and I'll show at the end, we've actually been working with Ford to deploy this on their next generation vehicles. And I'll speak about that near the end of the talk. We've actually, again, in this instance, compared to a bunch of different methods here. And I'll just sort of jump ahead here. RTD is our method. Again, it runs really, really fast. It's able to complete the track really well and doesn't run into any crashes, and it doesn't safely stop. Because it's always getting to the goal, so it doesn't have any issues there. Let me, in the last 10 minutes, briefly speak about how we can accommodate dynamic environments. So in this context, I may have a vehicle that's moving. The first assumption I'm going to make, and it's a really strong one, is that I'm going to assume that the predictions we're handed are conservative and contain the true behavior of the obstacles. Okay, that's a pretty drastic assumption, but if you really want to say something about safety, you need such an assumption. In fact, you really need something more, because it's really difficult to say something about safety if other people around you are malevolent. So I could be in a parked car, and I'm sure this happens at UCLA. You're in a parked car is parked, and someone runs into you, right? I know it happens here in Michigan because our roads are small sometimes. And, again, it's not the parked car's fault, but the parked car certainly cannot assert anything about the safety of its behavior. And so what we're going to do now is switch our definition or our thing that we're going to target from safety to a notion of not at fault. We're going to say that our autonomous vehicle is not at fault at a particular time if it's stationary or not intersecting with any obstacles, okay? And so what we're going to do then is basically try to do real-time planning now in a not at fault way. And the thing to keep in mind here is that we can return back to this optimization problem that I showed earlier. And in fact, we have this function v, which I said behaves like a Lyapunov function. And what that means in practice is that, if I have a time, a state, and a trajectory parameter, and it belongs to the forward reachable set, now I've made the forward reachable set a function of time, well then, in fact, this function v is going to be less than or equal to 0. So in fact, v is an outer approximation, or it's v's 0 sublevel set is an outer approximation to the forward reachable set of the system. And so what that means in practice is now I can use v as I was using w earlier. And the thing to keep in mind is that now I have these predictions, and these predictions, may be buffered at a particular instance in time by this buffer beta, and there may be a point spacing r for a particular instance in time, but I also need to make sure that I'm accommodating prediction error between, or prediction spacing between my forward reachable set and my prediction itself. And so in fact, what we do, or what we've done, is actually extend everything that I described earlier to account for the fact that I have discretized predictions now, and actually ensure that I'm safe across these sort of discretized predictions by enforcing sort of a time discretization that can ensure safety in general. And that's a function of sort of the maximum speed your vehicle is able to travel. And so we can write down this really nice theorem here that suppose the vehicle is convex and the maximum relative speed between any obstacle in the vehicle is bounded, then in fact there exists a time discretization that can be computed offline that generates an outer approximation of the set of safe trajectory parameters, or set of unsafe trajectory parameters, I should say. So that's a typo there. So again, we can take everything that I described in the earlier portion of the talk and apply it in the same way to this situation. And in fact, that's what we did. We worked with the University of Sydney, and we actually put everything that we'd done on a nice platform there. And in fact, it was supposed to be running a taxi service down there. COVID has slowed us down a little bit, but in fact, this is operating on their quad. We're going at about 4 or 5 meters per second here, which is about the speed limit of what we'd want to do on this quad anyway. And again, what you're seeing is it fully autonomously going around sort of this dense environment. You see people walking around, and we're actually generating predictions of them and going around them as well. And so this is really cool. Again, we can make some strong guarantees about safety in this instance. And in fact, we've extended it to other scenarios. So here's an example of doing an unprotected left turn, which tends to be pretty hard for autonomous vehicles. So we have these predictions. And in fact, our vehicle is able to plan around these predictions and get through sort of left turns like the following. And in fact, we've run it on a bunch of different scenarios. So here's some statistics on this particular example. And in fact, we compared it to a linear model predictive control method. And in fact, we can show that we can get to the goal 100% of the time, or nearly 100% of the time, with a fairly high speed. And our time to goal is pretty reasonable. What I'll mention is that we've run a bunch of comparisons here. So I'll just sort of quickly go through this. So we've done dozens, more than dozens of comparisons, but here are a few illustrated. And in fact, we're always able to say something about safety. So I'm not even going to include a crash thing here on the right-hand side. But in fact, we're not conservative while actually getting to goals. And that's a really important feature to have. You don't want to be, burdened by, being so concerned about moving that you never move at all. That is a way to ensure safety, but it's not a way to deploy an autonomous vehicle that's actually useful. And so our system is able to always get to goals and usually does better. I think this RRT is one rare example here, but almost always is doing better than every comparison, but can ensure the safety of the system while doing it. And as I mentioned, we've actually been throwing this on the autonomous vehicle that we have here at the University of Michigan. And in fact, we've been working with Ford Motor Company to actually deploy this on their vehicle for broad deployment as sort of like an autopilot feature as they move forward in their vehicle planning calendar. So I'll conclude here by mentioning that we've applied this framework to lots of systems. So this is an autonomous vehicle sort of talk, but I'll mention, we've done this with quad rotors. So here's an example in my lab. Again, not too large. So getting above about 1 meter per second is fairly difficult, but all the planning, everything is happening in real time here, and it's deciding to get from the start to the end. And you'll see sort of we're able to do all sorts of complex scenarios. So again, start and goal. Can jump ahead here maybe. So here's an interesting scenario where it's like a slalom that it has to run. I think we'll see an example in a second of moving obstacles. So here's a rover that is going to try to antagonize this poor quadrotor. And, it'll behave particularly mean to this quadrotor. And can jump ahead. I think you'll actually start seeing people appear in a moment. And hopefully these videos are actually playing, by the way. Okay, so here are some students who braved to stand in front of this quadrotor as it walked past them. And the thing to keep in mind is that this quadrotor behaves fairly aggressively. Like it tries to get close to people in a way that it can accommodate their predictions that we have for them and actually get to the goal in a reasonable way. So here we go. Usually the thing that everyone says about these sorts of reachability tools, by the way, is that, these are really cool, but they don't really work for complicated systems. High dimensional systems tends to be a big challenge for these things. Well, we wanted to prove everyone wrong. So this is a 7-DOF robot. So it's actually a 14-dimensional state space model. We're actually doing the same reachability-based trajectory design here, The reachable set here is drawn in these sort of gray lines in here. The high-level waypoints are drawn in black here. You'll notice they're in collision quite a bit. In fact, in this instance, we're computing the reachable set online. So earlier on, everything I described was offline reachable set computation. We're actually doing online reachable set computation here. This is a 14-dimensional reachable set that we're constructing online while doing real-time planning. So we've gotten really good at constructing these reachable sets. This is great. Just to make it even more interesting, here's Cassie. This is a 36-dimensional or 32-dimensional robot. We're constructing a 32-dimensional reachable set for this system. We've gotten really good at this. And this is quite exciting for us. This was pre-COVID. Hopefully we'll have more to say as we go on. I'll stop here by saying, RTD enables sort of collision-free or not at fault planning. We've, again, done this across a variety of different platforms. The questions that remain for us in an interesting way are how to think about perception and prediction and how to incorporate models of uncertainty. And I saw Luca Carlone gave a really nice talk, I think on Monday or Tuesday. Luca's thinking about some of these problems, and I think some of the stuff he's been doing has been, really relevant and applicable to these kinds of problems. These are the people who actually do the work. These are our sponsors. These are a bunch of different coding, software platforms or software toolboxes that you can, or repos that you can go and download. They have all of the code that I've described from all of this talk. So again, you can look here. That's where all the software is. Go download, play around with it, tell us what's wrong. We'd love the feedback. And that's all I have.